Your LTR model may be winning for the wrong reasons. This is the pattern you'll be able to implement by the end, which removes features one by one and reports the signals that raise the relevance score. I'm Professor Pi, teaching search and IR with simple Python. Learning to rank feature ablation with LightGBM solves a practical problem. Teams build complex ranking models with dozens of signals. The model may score well, but some signals can hide biases or leak labels. Success is a model that wins for robust relevance, not for an accidental shortcut. LightGBM is a fast gradient boosting library that supports ranking objectives. It fits small to medium datasets quickly and makes retraining ablations practical. The intuitive idea is simple. Train a ranking model with all features and measure NDCG, which is a score that compares the actual ranking to an ideal ranking using discounted gains. Then, drop one feature, retrain, and measure again. If removing a feature improves NDCG, that feature was hurting generalization. If NDCG drops, the feature was helping. The goal is to reveal which signals truly move search quality. We will build a tiny toy ranking to follow the full loop. It is small, so each step is clear. You will see a baseline score from one feature, a LightGBM model trained on all features, a per-feature ablation, a validation-aware setup with early stopping, and finally a validation-driven ablation choice. Now we'll build the tiny toy ranking and compute a baseline. This snippet builds a tiny ranking example with 5 documents and 3 simple features, then computes a baseline NDCG at 5, using the first feature as the score. The array Y holds graded relevance labels, while X stores feature values per document. We sort documents by the first column in X, interpret that as a ranking, and calculate DCG using logarithmic discount factors in C. The array O captures the ranked positions, and IDCG is the ideal gain from sorting by true labels. Dividing DCG by IDCG normalizes the score to the 0-1 range. The printed value shows how strong that single feature is as a ranking signal. Next, we'll train a LambdaRank model in LightGBM on the same tiny set. This example trains a learning to rank model in LightGBM and evaluates NDCG at 5 on the toy data. We wrap X and Y in LGB.dataset with a single query group, then set the LambdaRank objective and NDCG at 5 metric in params. The call LGB.train fits boosted trees, and model predict returns per document scores that we sort to compute DCG and IDCG with the same NumPy logic as before. Comparing to the prior baseline reveals whether combining features beats any single signal. Increasing NumBoost round can raise the score but risks overfitting tiny sets. Decreasing it reduces capacity and may underfit. The printed value reflects ranking quality using all available features. Now we'll run a single feature ablation loop to see which drop helps. This code runs an ablation in LightGBM to reveal which single feature degrades ranking when removed. The list names maps columns to human-readable feature names. For each feature index, np.delete drops that column from X. LGB dataset wraps the reduced matrix, and LGB.train retrains a model. We predict with the ablated model, recompute NDCG at 5 by sorting its scores, and record the result in scores. We then select the drop that improves NDCG the most relative to the base score from the full model. Larger NumBoost round can exaggerate differences. Smaller values stabilize comparisons. The printed output spotlights the feature whose removal helped performance the most. Next, we make evaluation more realistic by adding a second query, and using early stopping on a validation split. This snippet upgrades evaluation by introducing a query-wise validation split and LightGBM early stopping. We append a second query to X and Y, then slice indices so the first query forms training and the second forms validation. Two LGB dataset objects carry the grouped data into LGB train, which uses valid sets with LGB early stopping to select the best iteration. We score the validation query with model.predict at best iteration and compute NDCG at 5, using the same NumPy DCG and IDCG math. Longer patience can fit deeper, but risks overfitting. Shorter patience stops earlier and may underfit. The printed value reflects realistic generalization to an unseen query. Finally, we'll pick a feature to drop based on validation performance and retrain fairly. This example performs validation-driven ablation in LightGBM to choose a feature to remove before retraining. We reuse model.bestIteration as a fair training budget, ensuring each ablation compares at the same capacity. For each feature, NP-delete creates train and validation matrices without that column. LGB.dataset wraps them, and LGB.train fits a new model. We rank validation documents with mv.predict, compute NDCG at 5, and keep the best post-drop score only if it exceeds the current validation baseline. Larger num boost round can make weak features look helpful by overfitting, so fixing rounds improves fairness. The printed result names the drop choice and its validation NDCG gain. In a real project, this tiny loop maps directly to a holdout pipeline. Replace the toy queries with batches of real queries, keep groups for each query, and run the same ablation logic. The same fairness tricks apply. Use a consistent training budget for all drops and validate on genuine unseen queries so you do not reward features that only memorize noise. Recap what it is: a drop 1 ablation that retrains LightGBM and compares NDCG to find harmful or redundant signals. When to use it: when you suspect feature leakage or want a cleaner, more robust ranking model. One caveat: small datasets can overstate effects, so prefer validation-driven decisions. Next step: tune num boost round and early stopping patience while keeping the budget fixed across ablations to balance capacity and fair comparison. If short, practical IR helps, subscribe and watch the IR videos.